All right, we're going to dive back in, guys. We're going to deal with now weak acids and weak bases. And the key is a weak acid, weak base, they don't dissociate completely. And so we're going to talk about how much do they really dissociate then. And so in this case, a generic weak acid we'll call HA. HA, generic weak acid. And when it dissociates, we can describe that in one of two ways. We can describe it dissociated into H plus and A minus, or we can actually show how it's reacting with water. And it still forms A minus, but instead of H plus, what do we get now? H3O plus. And like I said earlier, H3O plus and H plus, they're directly analogous. They really stand for the same thing. So, and in this case, if we show all the phases, so what would the equilibrium constant, Kc, for this reaction look like? What would the expression look like? How would that change if I wrote it this way? Wouldn't. Instead of H plus, we might say H3O plus, but again, those are the same thing. Water being a liquid doesn't show up. Cool. This particular Kc, when it's for an acid dissociating in water, we call Ka. So Ka is an acid dissociating in water reaction. Kb, as we'll see, is a base dissociating in water reaction. Cool. Some of the questions you commonly get that are more conceptual rather than calculation might ask you to either write the reaction or write the expression for a specific acid. So notice, let's say I said, give me the Ka expression for HCO3 minus. And this is where it gets tricky, because this particular substance could act as an acid or a base. It is, again, what is the word? Amphoteric. Amphoteric. So in this case, if I'm going to talk about Ka, then I'm talking about this compound acting as what? An acid. And so in this case, again, I can include the water, but I don't have to. And if I have it acting as an acid, it donates an H plus out into the solution. And what will I be left with? And so they might look for this reaction, where the Ka reaction for HCO3 minus, that would be it. Or they might look for the Ka expression. And in this case, what would that Ka expression look like? Cool. All over? Awesome. And again, instead of H plus, it could have been H3O plus, same diff. So they may get generic, and this is what I'm going to use to do some calculations, or a simple question, and I say it's simple, but at least it's not a calculation anyways, might just be write the Ka reaction or the Ka expression for a specific acid, the bicarbonate ion in this case. Cool. We can do the same thing for weak bases. So for a weak base, in this case, the weak base I'm going to choose to use is generically A minus. And I chose him because he's the conjugate base of my generic weak acid HA. So when you're looking at the reaction of a weak base, though, you have no choice but to include water. And again, from a Bronsted-Lowry perspective, what's a base? Proton acceptor, proton acceptor. And so in this case, if I'm going to show him accepting a proton, well, I got to show where he gets it from, in this case, the water. So I got to include the water in this case, no choice with the bases. In this case, what do I get? I get hydroxide. Once we get an H from water, we get hydroxide and? Cool. And the equilibrium constant expression for this, and actually, why don't we do this over here? We'll call Kb. So for a base dissociating water, what is the expression here? I'll write it the other way, but same diff. Cool. And again, just like we did this for weak acids, I could give you a question, or whoever, Dr. Searley could give you a question that says, show me the Kb reaction or the Kb expression for a specific weak base. And I'm going to ask you, what is it for ammonia? And so in this case, well, it's ammonia plus the water. You got to include the water. And what are we going to get? Still get hydroxide. Good. And after picking up an H+, NH3 turns into NH4+. And what would the actual Kb expression be? Cool. Any questions on just this so far, Ka and Kb, how we derive them, what they represent? Okay, there's one more part to this. When you look at the Ka of an acid, in this case HA, and you look at the Kb expression for his conjugate base, A-, has to be his conjugate base, then we can look at the Ka of the acid times the Kb of the conjugate base. And if you multiply the Ka expression of an acid times the Kb specifically of his conjugate base again, what cancels out? So this times this. Yeah, don't just say acid and base, because that's a little generic, because HA is an acid, but H+ is also an acid. So we can't just say acid and base, but what specifically cancels out? HA is going to cancel, and A- is going to cancel, and what are you going to be left with? H+ times OH-, but we already know what that's equal to at 25 degrees Celsius. What's that equal to? Yeah, that's equal to Kw. So you often hear people say that Ka times Kb equals Kw. Cool. This is convenient. This is one way of demonstrating that the stronger an acid is, the weaker its conjugate base will be. The stronger a base is, the weaker its conjugate acid will be. Because if Ka is higher, that's going to mean a stronger acid. But if Ka is higher, then Kb for the conjugate base is going to have to be lower. So a stronger acid means mathematically a weaker conjugate base. This is always true. Cool. So if you look at this now, so a larger equilibrium constant means we're going to get it more what? More acidic in this case, but in general more products, which in our case the products are H+, so more acidic for an acid, or in the case of a base, more OH-, so more basic for a base. So the higher the Ka, the stronger the acid. The higher the Kb, the stronger the base. Okay? So a couple different questions I might give you. So a couple questions you might get now using Kas. I might say, which of these three acids is the strongest? Just based on giving you Ka values. Which one's the strongest? Yeah, HF is the strongest. So, and be careful, because a lot of students see when it's the same power, they get confused. Because usually a more negative power means a smaller number, and a less negative power means a bigger number. And because of that, they forget that, well, the number part, those are just numbers, though. And 6.8 is higher than 1.8. So don't get lost on that. And so in this case, the strongest acid, yeah, he wins. HF wins. But the other question you might get instead is you're still given this table, but the question says F minus C2H3O2 minus CN minus. And the question is, which one of these is the strongest base? Good. CN minus. Why? Because its conjugate acid is the weakest of the three. And so its conjugate base must be the strongest of the three. Stronger the acid, the weaker the conjugate base, and vice versa. Cool. I want to dispel a rumor for a minute here as well. We'll visit this again a little bit later. I'm going to dispel this rumor later. Never mind. You guys ready to move on? Okay, let's do some calculations. All right. First problem on the backside. You are told that the Ka of acetic acid is 1.76 times 10 to the minus 5. And the question is, what's the pH of a 0.1 molar solution of acetic acid. I'm just going to abbreviate it as HAC, and truth be told, for the calculation, I'll probably just call it HA. So to get pH, what am I probably going to use to actually solve for pH? Which of the 4 things we can calculate? H plus. I want to solve for the H plus concentration because then I can take the negative log of that. So to get there. Now what will the H plus again not equal? Being that it's a weak acid. It's not going to be 0.1. Doesn't dissociate completely. So, but how do I actually figure out what it is? Well, I got good news and I got bad news. And I'm going to give you the bad news first. Remember these? That's the bad news. So in this case, what is the initial concentration of our acid, HA? 0.1. So, and the H plus and A minus? Essentially 0. Truth be told, pure water does already have a little bit of H plus, but we'll ignore it anyways. It's going to be insignificant. Cool. What's the change in the concentration of HA? Minus X, H plus and A minus? And so at equilibrium, what's the concentration of H plus? X. Notice, again, let's not lose sight of this. The whole point in setting up this ice chart is I want whatever goes in that box right there. Because I want the H plus, because that's what I'm going to use to get the pH. So what's the equilibrium concentration of A minus? X and HA? 0.1 minus X. And I'll plug these equilibrium values back into my Ka expression. And so in this case, Ka is 1.76 times 10 to the minus 5. Oh, and I totally jacked that on the chart over there. It's terrible. So in this case, the H plus concentration is X. A minus concentration is X. And the HA concentration equilibrium is 0.1 minus X. Cool. What is the most mathematically sound way of solving for X? What's that? Yeah, quadratic. And will you ever have to use the quadratic, though? No, and this would be an example where you wouldn't have to. How do I get around using the quadratic? Yeah, we're going to ignore this little minus X. We're going to assume X is so small that when I subtract it from 0.1, I still essentially get 0.1. So is there any reason to expect X to be small? Yeah, I got a really small Ka value. If you have a small Ka, that's evidence that your reaction favors the reactants. And X here represents how much of the reactants reacts. Well, I got all reactants initially, all reactants. And when I'm done, I'm still going to have mostly reactants, so I expect the amount that actually reacts is going to be small. So a small Ka usually means a small value of X as well. Cool. So it turns out this will end up being a good assumption, but you guys, not ever having to use the quadratic, can always assume it's a good assumption. How tiny? So for you guys, you know you never have to use the quadratic. We're going to take advantage of that in a little bit, but the truth is, if when we solve for X, if X is greater than 5% of what you're subtracting it from, then it's probably a bad assumption. It's got to be less than 5% of 0.1 in this case. And it will be, so because she's not going to give you one that's not. Exactly. So for the test. Now mastering chemistry, they may ask you some where that'd be a bad assumption. But on the test, no quadratic. Cool, so if we solve this, you multiply it by 0.1 over here, and then take the square root, because this is like x squared, right? And can somebody get me a value of x? And again, what's my goal right now? Get the H plus. Well, ultimate goal is to get the pH. And how am I going to get there? By getting the what first? H plus, which just happens to equal x. So this also equals H plus. Now, if you recall from the beginning, we already said we knew what the H plus would not equal. And from the very get-go, we said H plus would not equal, wasn't going to equal 0.1. We knew it would be less. And we just verified that, yeah, it's less. And in fact, it is, this number is, if you divide this by this and multiply by 100, you'll find out it's only 1.3% of 0.1. It's less than 5%. Great assumption. And if we take the negative log, what's the pH? Awesome. So that's the bad news. We had to use an ice chart. Now you want the good news? The good news is we just said you never have to use the quadratic. And if you never have to use the quadratic, we can shortcut this process a whole lot. So notice we made this x times x, right? Because they were both equal to x. Do I have to use x's? What if I wanted to use y's? Is that okay? What if I wanted to use q's? Cool. What if I wanted to use like an unpronounceable symbol? I use whatever I want, right? Here's the deal. What's important, though, is that these two concentrations are equal at equilibrium. And so in this case, I'm going to rewrite this expression here. You guys will see how lucky and fortunate you really are here. So in this case, Ka, instead of writing this as H plus times A minus, we wrote it as x times x last time. I could have been y times y or q times q. Well, what am I ultimately trying to solve for here so that I can get the pH? What am I ultimately trying to get so I can get the pH? H plus. Well, then why even put in x's? I'm just going to call it H plus times H plus since they're equal. And we'll call this H plus squared. Cool. And then over here, it's HA on the bottom, but it's the HA at equilibrium, not the original concentration, but the HA at equilibrium, which means that has to factor in the minus x. But are we ever going to factor in that minus x? No, then you can just actually use the initial concentration of HA. This shortcut, if we rearrange this and solve for H plus, you'll find out that H plus equals the square root of Ka times the initial HA concentration. It's an approximation here. I really should say approximately equal. And then you take the negative log and get your pH. It totally skips the entire ice chart. I think it would be a very good idea if you memorize this. She's not going to give this one to you, but you can spend 5 minutes setting up an ice chart and solving this one, or you can take 30 seconds and plug it in. This only works because you guys know you will never have to use the quadratic equation. She'll never give you an example on the test where you'd have to use that. If you were in a class where a professor totally loved the quadratic equation, you couldn't use this shortcut. It wouldn't work for you. You'd have to do everything for an ice chart, and then you'd have to look and see, was it a good idea to ignore x, yes or no, to decide. It'd be a big pain in the butt. You guys are super lucky. Cool. So notice if I said, what's the pH of a whatever concentration solution of a particular acid and gave you the Ka. Well, the two numbers I gave you were the concentration of the acid and the Ka. And multiply them, square root, and you have your H plus. Take the negative log, you got your pH problem done. And so what initially was a long ice chart problem is now much, much shorter. Question?
It works the same for bases.
Totally works the same for bases. So what would it be for bases? Awesome. Totally works the same way. So if you notice, the strong acid problem, that was an easy problem because it just dissociates completely and you just take the negative log and you're done, right, to get the pH. The strong base problem was almost equally as easy because it dissociates completely and you just take the negative log of your hydroxide, get the POH, and then subtract from 14, get your pH. But the weak acid and base were a little bit harder if you go all the way back to the ice chart. I wanted to set one up so that the process makes sense. But once you really reduce it down to this, your life is a lot easier, and it's not such a bad problem anymore. Cool. These are now 4 out of the 5 types of problems. Let's work the last couple examples on here that are just a little bit backwards. So you're still going to want to know your original Ka expression, by the way, but you're also going to want to know shortcut. The shortcut's really handy if you're solving for what again? pH, because you're going to get the H plus first. But not every problem is what is the pH. So look at the second problem on your handout there. It's labeled as part B. It says, what is the Ka of a weak acid HA if the pH of a 0.1 molar solution equals 3? So the pH of a 0.1 molar solution equals 3. Okay. It's not saying what is the pH anymore. They want the Ka. They want this guy. So, and I'm going to use the original Ka expression to do this problem. So in this case, the Ka, well, the pH, in fact, maybe I should write this just a little bit different so we know this is the pH. It's a 0.1 molar solution, and again, the pH is 3. Why is this useful? What does this really ultimately give me with regard to Ka? Gives me the H plus concentration. But the H plus concentration is also equal to the A minus concentration, which also happens to be X. And so in this case, your Ka, again, is equal to H plus times A minus over HA. And we can see from the same ice chart here, so that's equal to X times X. But if the pH is 3, the H plus is 10 to the negative 3. And so in this case, that's 10 to the minus 3 times 10 to the minus 3 all over what? Point 0.1 minus 10 to the minus 3. And you got to be like, wait a minute, Chad, you just told us to ignore this. I told you to ignore it here because that allowed me to avoid what? The quadratic equation. And does that put a little bit of error in my calculation? You bet. But it's hopefully going to be, always, in your example at least, an insignificant amount of error. But here, does ignoring this make me avoid a quadratic? No, whether I include it or not, I don't have to use a quadratic. So she could give you this question, and if you didn't include it here, it could be an example of where it was significant enough that if you ignored it, you got the wrong answer. So the only time you want to ignore it is if it helps you avoid the quadratic equation. It doesn't help me here. I'm going to get a more exact answer by including it. Truth be told, it's rather insignificant here as well. 10 to the minus 3 is only 1% of 0.1. So can somebody get me my Ka value here?
1.01 times 10 to the negative 5.
Awesome. So the two big things you really want to know are the Ka expression, again, the generic Ka expression, and the shortcuts. The generic Kb expression for weak bases was, we'll see, and the shortcut. Cool. If you're asked for the H plus, use the shortcut. If they say solve for Ka, use the original. Cool? Okay. We got one more question here about a weak acid. And the question is, for this weak acid we just dealt with in part B here, what is the percent dissociation of the acid? What is the percent dissociation of the acid? Well, if we look here, what's a percentage? So it's part over whole times 100. Sweet. That's what percentage is, part over whole times 100. So what if I told you that you've all been exposed to a dangerous gas, and this gas will make you dissociate? For lack of a better term, don't think about what that looks like. Cool, but I haven't perfected my noxious gas here that I concocted. I've already taken the antidote, I'm fine. And so that only 5% of you are actually going to dissociate. So out of the 20 or so that are here, one person will dissociate. You take the amount that dissociated, 1, divided by the total number of original people, 20, and you get your 5% after multiplying by 100, right? So that's percent dissociation. Well, here, for a weak acid, you take the amount that dissociated, which was X. So, and in this case, that's equal to the H plus concentration. Divide it by the original total amount of acid, and then multiply by 100. And so in this case, your percent dissociation, again, is part over whole times 100. And in our case, this reduces down to the H plus is equal to the part that dissociated. The whole was the original acid, total acid concentration, and then times 100. And so for this last problem, what was the H plus concentration at equilibrium? 0.001, 10 to the minus 3. What was the total original acid concentration? 0.1. And times 100, and what was our percent dissociation? 1%. So that's how you do percent dissociation. Might also be called percent ionization, same diff. So, question. So, correct, because if it's a strong acid, I already know the percent dissociation. It's, oh, you can do weak bases as well. In fact, we've done all the weak acids. Now we're going to go do a couple weak base problems as well. So, you guys ready to do the weak base problems? Let's do that. All right, weak bases. If we look at weak bases, we're going to do the same thing we did for weak acids. Yes, you should know the general reaction and the general Kb expression, but if you're actually asked to solve for pH, you're going to use the shortcut. And again, why are you allowed to use this shortcut? What's the only reason? Because you don't have to know, you're told that you never have to use the quadratic equation. If you were told, again, if you were in a class where the professor liked the quadratic, you couldn't do this. You'd always have to set up the ice chart and plug it into the expression, and it would be a much longer process. But you guys get to short circuit that every time on the test. Okay, so the next question on your handout, part D, says what is the pH of a 0.1 molar solution of ammonia, and it gives you the Kb as 1.75 times 10 to the negative 5. Well, let me ask you a question. What are we actually going to be solving for a weak base initially in order to try and calculate the pH? Well, but what are we going to even do before the pOH? Just the hydroxide concentration. We're going to be solving for the hydroxide concentration and going from there. That's why the shortcut is set up to be solving for the hydroxide. This is what you want to use if you're on your way to solving for the pH, or the pOH for that matter, but it's usually pH. Okay, so to get my pH here, we're definitely going to use this lovely shortcut. And so again, your hydroxide concentration is equal to square root of Kb times the original base concentration. And so in this case, the Kb is given, and the original base concentration is given, and it's plug and chug. Somebody get me an answer for that. I picked the numbers conveniently so that it would come out pretty close to the last one. 0.00 what? Good. Looks familiar, doesn't it? And so then what can I get from here? pOH, and what's the pOH? Pretty similar to what we did before, and it's going to be 2 point what?
88.
Yeah, I'll round it to 2.9. And so then what's the pH? Anybody? Awesome. And notice again, because you're allowed to avoid the quadratic, I totally went to the shortcut. I skipped the whole ice chart. But technically, for anything that's only going to dissociate partially, it's an equilibrium problem. We were technically supposed to deal with an ice chart. We just kind of short-circuited the process, saved ourselves some time. All right, part E. Part E, what is the question actually asking you to solve for in part E? Kb, so then should you use the shortcut? No, the shortcut's how you get OH minus. To solve for Kb, I should just use the original Kb expression. And so in this case, question says, what is the Kb of a weak base, A minus, if the pH of a 0.1 molar solution is 10.2. This is about as hard as they get. Truth be told, it's not any harder than the problem we had before that said, what is the Ka? Except for one little thing. We're given the pH, but what is the pH ultimately going to help me get in this process? The OH. How do I get there? So not the negative log. So, and I could do 10 to the negative, but I probably, instead of pH, I probably want to get what first? pOH. And what is the pOH? 3.8. And so then the OH minus concentration would be 10 to the negative 3.8 molar. And you could use your calculator to tell you what that is, but we're just showing our work now. It's not the answer we're looking for, so we're good to just leave it like that. And in our case, that's what we're going to plug back into the expression. Kb here notice, if you recall, if all you started with was a weak base, then these two concentrations should both be equal. And now we just found out they're both equal to that then. And so we have on top here 10 to the negative 3.8 times 10 to the negative 3.8. What was the original base concentration on bottom here? 0.1, and technically it's 0.1 minus the amount that reacted, 10 to the negative 3.8. But again, in this case, it's one of those ones that will be insignificant, but we don't avoid the quadratic by leaving it out, so we should probably just include it in just in case. And can somebody get me a KB? Anybody? Sounds about right. Awesome. Questions? Now we've done 4 out of the 5 types of problems. Strong acid problems, strong base problems. Weak acid problems, weak base problems. The other main type of problem we'll end up dealing with are buffers, but we'll deal with those a little bit later. Cool. So, and again, I heard some of you guys complaining when you first walked in about timing as an issue when taking the test. And that's always an issue. So not just in Gen Chem, in OChem, it'll be the same issue again. So the only way to get good on timing is to do a million problems. So one of the hard things that makes it hard in this chapter is students often don't even realize what kind of problem they're being asked. If it was told them there's only 5 real types of problems, and they knew each of those 5 types inside and out, then as soon as they read a question, they'd know which one it was. Is that a strong acid? Is it a weak acid? Is it a strong base? Is it a weak base? Or is it a buffer, as we'll see later? So, and technically, or is it a titration problem, which reduces down to one of those 5 types? So, but once you realize that, it's not so bad. So, but you got to work at problems. This is really like a math class. So, and if you know how to do, whatever, say you know how to do all the integrals, but you've only done one example of each type of integral, you'll never finish a test on time. Same thing here. There's 5 types here. If you've only ever worked one of each of the 5 types, you're never going to be able to do the calculations in the time you need to. So work a ton of examples right out of the back of the chapter of all these different types of problems to the point where you get good at recognizing even what type you're doing. Cool. Ready to start with a clean slate?